This does not look good for you.
I'm pickpocket. I stole the bag, but I didn't know there was a bomb in it.
But you ran. Innocent people do not run.
You were coming after me. Have you seen yourself?
Must be really good.
I'm the best.
Just walk up to me and steal my wallet. Still there.
But the money's gone.
Me, la 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 la. Let's go. In this video, I'm trying to explain how you calculate some scales to show the exact heat transition between inside, outside, and the components of a wall. First of all, you have to work out the heat transfer resistance R of the components of the wall. Therefore, you need the component thickness and the thermal conductivity. You find the thermal conductivity of the component in a chart. Then you divide the thickness by the thermal conductivity. As you can see at the formula, the resistance is getting higher when the wall is getting thicker and lower with a higher thermal conductivity. The thermal conductivity is a measured value and is affected by some characteristics of the material. Some of these characteristics are the structure, porousness, gross density, moisture content, and the temperature. If the material has a low gross density, there are many voids in it. More voids means more air. Air has a thermal conductivity from 0.022 watts per meter Kelvin. That's really low, but as I mentioned earlier, a low thermal conductivity results a high transfer resistance. We learned now that many voids with air are a good thing. But if you build a wall with a high amount of voids, as a mineral wool, you have to protect it from water. Because if water entered the voids, the air is pressed out, and water is the new major constituent. Water has a thermal conductivity from 0.6 watts per meter Kelvin. Just as a reminder, air had 0.022. To come back to the calculations, we had the formula for the transfer resistance R. With the calculated R, we can now find out the heat transition coefficient, U, by dividing 1 by the sum of all the resistances. In our example, we have 3 components, as you can see, but we also have to respect the heat transfer between the last component and the air, because the small air layer on the outside of the wall has also a heat transfer resistance R. That means we have 5 R's that we have to add. Done with that, we can calculate the heat flux density Q by multiplying the transition coefficient U with the temperature difference delta T. We calculated now the heat transfer resistance R, the heat transition coefficient U, and the heat flux density Q. With these formulas, we can determine, for example, the minimum thickness of a used material to achieve the willing heat transfer resistance R. As a last step, we now show the exact heat transition between the in and outside of the wall. We do that, for example, to determine the exact spot in which the temperature reaches 0 degree, or to see where we have a critical point with dampness. You start at the layer transition outside and add always the current temperature from the point before to the multiplied R and Q. If you calculate it through the end, there should come out the current temperature inside. To exemplify the whole thing I explained, I'm doing now a small experiment with my own wall in the living room. Of course, there are many factors that falsify the experiment, but the fact that our heating installation isn't working in our living room since 1 year is helping us in this situation. As you can see, is the current temperature 17.4 Celsius. If you try to calculate by yourself, next to it, you're welcome to stop the video after the steps. First I calculate the R's, then the U. With the U and the inside temperature of 17.4 degree and outside of 8 degree, we have the Q. In our last step, we just calculate the heat transition from our layers. Therefore, we just put in the values in the formula. As you can see, we have now a temperature for each layer. If we want to illustrate it, we just go back to my wall and draw a curve with the solutions in the picture.